reducing sediment and phosphorus export in small Swedish agricultural catchment. So this work we did with our colleagues at the Swedish University of Agricultural Sciences in Uppsala. And our research is funded, as part of the Bell's Talent Program funded by the European Horizon 2020 project.
Fine. Something weird happened.
Okay, so
I can pass.
yeah, my presentation will follow this context from introduction, objectives, methodology, and then discussion and finally conclusion.
That was working.
Yeah. So, as we all know, agricultural activities contribute significantly to polluting water resources, especially through the runoff of sediments and nutrients or chemicals from fertilizers or pesticides and so on into receiving water bodies like streams and so on. However, to get sustainable agriculture, we can use best management practices to be able to minimize some of these activities. And so, to understand how these best management practices can help in reducing, before implementing them physically, we can use mathematical models such as the SWAT model that we used here. So the motivation of the study is because the study area that we are working on is one of the 21 small agricultural monitoring catchment that they carry out very intensive monitoring within Sweden that divided into several different areas. It's in the study area. And they have been doing monitoring for the last 3 decades since the 1990s. And this particular catchment was of interest to us because it has very high phosphorus losses. The catchment, and it's the second highest amongst the 21 catchments, and it has been seeing quite an increasing trajectory in phosphorus, as you can see here, which currently is almost at 0.35 or 0 point something, compared to the less than 0.2 from the average of the entire region. However, the nitrogen losses are a bit low, so we were not really interested in the nitrogen losses. That's why we only did the sediment and the phosphorus losses. And this study will be contributing to the Swedish Environmental Protection Agency target of reducing phosphorus levels by at least 50% by 2027 in order to achieve the Water Framework Directive of good ecological status and hopefully someday achieve zero eutrophication. So the objective of this study was to evaluate the application of SWAT model in this watershed by calibrating and validating the model for stream flow, sediment, and phosphorus, and then using the calibrated model to quantify some agricultural BMPs effectiveness in reducing sediment and phosphorus in this area, particularly the soluble and total phosphorus in there. So our study area, as I said, is part of the 21 different agricultural monitoring area, and those monitoring areas are within each of these regions. So these regions are called leaching regions or leakage regions, where nutrients leakage has been identified, and they have small catchment in each that they do the monitoring. So our catchment is here, C6, so it's named C6, it's leaching region 6. And this catchment is predominantly an agricultural area. The yellow part is an arable land where they do a lot of agricultural cultivation, mainly cereals. And towards the periphery, we have forested areas around this region. And the soil in the area is mainly clay soils, post-glacial clay soils, with predominantly silty clay within the agricultural area of the cultivated area, while towards the forested land, we have clay loam soil. The area is about 33 square kilometers, so it's a small catchment, and has a generally flat land. More than 80% is less than 2% slope, and the rainfall is about 500 millimeter. Temperature is very cold during winter and moderately warm summer. So to set up our model, we did the normal SWAT model setup. So we started with our model inputs of the land use and map, methodological data, and the agricultural management information. And then we created the model by generating 32 subbasins and 349 HRUs. And then to evaluate our model, we ran our model from 1990 up to 2000. And we did our calibration from 2005 to 2012, and then model validation from 2013 up to 2020. And we calibrated our model using the stream flow, sediment, and total phosphorus. And then for the best management practices, so we implemented different scenarios, mostly dealing with structural measures, because in the catchment, they are already doing some nutrient management measures. So we wanted to see alternative measures that could probably work, because it seems the nutrient management measures are not really much effective at the moment for that. So we implemented filter strips, sedimentation ponds, grass waterway, and not tillage. So to implement our scenarios, we modified different parameters in the model based on the available literature for SWAT. And for filter strip, we kind of analyzed the width, changing different widths until we got an optimum width. So we looked at different widths from 5 to 10 meters on which how they reduce the sediment and phosphorus. For grass waterway, we use parameters for channel cover and also the margins value for the channel and so on, and erodibility also. And the sedimentation ponds, we use the sedimentation pond parameters that are available. And no tillage, we used the no tillage parameters based on the no tillage database that's available for SWAT. So for our results, the calibration was quite good, and stream flow had the best calibration. Yeah, we had over 0.8 lysatkins. Also the R squared, P bias, and the other performance metrics are quite good. And same with the sediment load, we had almost 0.65 and above, which we regarded as quite good for our study area. And the total phosphorus was also quite good. But we could also observe a bit of underestimation by the model. And this is something that I've always struggled with SWAT, even in other projects. It's always tend to seem to underestimate sometimes a lot, especially for our total phosphorus, we could see a bit of underestimation. And for the parameters, in most sensitive for stream flow, we had the snow parameters. This area snows a lot during winter, and so we had to set our snow parameters well. The groundwater parameters are also more sensitive here because there is a lot of drainage in this area, and so we also did a bit reduced to increase water entering because of the clay, so it takes a bit longer time to penetrate, but with the drainage it goes very fast. And then the soil properties and land use management are also sensitive for stream flow. For sediment, we have channel properties and routing, sediment routing properties. And then we have also this phosphorus related parameters that were sensitive for our model. So for the spatial distribution of phosphorus within our catchment, we could see that the organic and sediment phosphorus were mainly predominant in the forested areas, the periphery where forests are high, but within the areas where arable land at the center here, it was mainly soluble phosphorus, and this is because of the use of mineral fertilizers here. So that's what we saw in our spatial distribution. So when if the focus is to reduce mineral fertilizer, then we focus on the arable land, while if it's about the organic or sediment, then it's better to work the forest together. So our best management scenarios, when we were analyzing, we for stream flow, we did not see any reasonable change, and except for the sedimentation ponds that had a slight reduction of about like 10%. But the others, filter strips and grass waterway and not there was no any difference at all. So there was no major difference for stream flow from all the stream flow reduction for all the BMPs. For sediments, you could see some reduction in others, while others like grass waterways and not there was no significant reduction, but for filter strip and sedimentation only reduced a bit. Soluble phosphorus, there was a great reduction, especially for filter strip and sedimentation pond, but not so much for grass waterways. And it was the same also for the total phosphorus. And so when we did a significant test to see how significant the reductions were, we only found that filter strip and sedimentation ponds were the most significant in reducing this, with the p-value less than 0.5. The others were not really significant in terms of the reduction. So for the specific reductions, filter strips reduced the 7.5 liter filter strip reduced phosphorus by almost over 65%, while sediments by just about 30%. Sedimentation ponds reduced the total phosphorus by 50%, while soluble phosphorus and sediments are reduced by just about 35%, 36%. However, we could see the effect of grass waterways was not so much. In fact, it was even increasing soluble phosphorus a bit slightly, by about 4%. Even though sediment was reducing quite significantly, but the total phosphorus, because it's a combination of both the soluble and the sediment, so it was not an organic phosphorus, it was not really much, 5%. And then for the notch-tillage, it was only effective for soluble phosphorus reduction by about 17, but not really in terms of erosion of sediments and total phosphorus, it was not really effective. And we looked also what's happening in different seasons, and we could see the reduction for most of these BMP scenarios was just similar for most of the scenarios, except for the grass waterways. We saw an increase in soluble phosphorus was much higher during winter, and no tillage during autumn, when most of the tillage always happen in this watershed. You could see a higher reduction in soluble phosphorus. Otherwise, the rest were just the same throughout the seasons. So for the filter strip, when we are looking at the different widths and their effectiveness, you could see the more we increase the width, the better the filter strip was. However, we saw an optimum filter strip of about 8 meters, which was reducing so well our sediment by almost 40%, and also reducing the soluble and total phosphorus quite good, almost 70%. Although the other strips were also good, we could see soluble phosphorus and total phosphorus reduction by filter strip is almost the same. So there is no significant difference between the two of them. So in conclusion, our SWAT model was very good at simulating this, so you can use it, you can apply it in this catchment. There was varying effects of BMPs in the catchment with filter strip and sedimentation ponds, reducing our sediment and phosphorus better. Based on studies of what we saw, we can regard sediment as the main driver of phosphorus exporters. The sediment of phosphorus attaches itself to the clay soil particles. And the effectiveness of filter strip for pollutant reduction increases with increasing filter width. And could be better to also explore in the future other BMPs and together with combination to see what could be the effects, and also do an economic viability and cost effectiveness assessment this BMP to really quantify how much money they can save by implementing these programs. Thank you very much.
The last presentation, and of course, the last question. Okay, I see three. So you was first.
Yeah, okay, thank you. Thank you for a nice presentation. And I was wondering, I mean, phosphorus is a difficult thing to model, and your validation result was good, but I guess the problem is when you have to include these measures in the model, how sure are you that you know they work as you think they work in the model? I mean, you're not able to validate the scenario results, like so many percent is for the measures are so good and so good, so it's model results. So well, what is my question? My question is, how sure are you that on the scenario results? I mean, actually, I think it of course the model is good and so on, but I think the problem is when you implement these things, how sure are you then?
Yeah, you're right. It's there is modeling, and then the actual implementation might differ quite a bit. The calibration and validation of phosphorus, it was a bit challenging, yes, but when we got these results, we thought, okay, these are the best line. We cannot be 100% sure that this will be, because there are different variations, especially because we are changing some parameters, we are just changing parameters here and there. And we hope, because based on literature, we have learned that these are the parameters that affect this kind of processes. So we hope, because these parameters are changed, that their effect will be represented on the actual, when you now do the actual implementation in the field, they will follow the same trajectory. Yeah, but we cannot be 100% sure, but we hope that's the case.
Okay, I think it.
Oh yeah, I was just wondering why your no-till was more effective for decreasing soluble phosphorus. Like, what's maybe what you think the mechanism behind that? Because in the, like I found in my model, when I increase no-till, it increases phosphorus runoff because you're no longer incorporating that phosphorus. So it's more susceptible.
Yeah, even for me, I was a bit surprised, because it was not decreasing total phosphorus and the effect on sediment, because we were attributing this effect on sediment, and sediment loss by no-till in our case was very negligible. But for the For the soluble phosphorus, we were thinking maybe it's because the time that it was reducing most during autumn is the time mostly they do the tillage. So they do tillage and that's where they plant. And so putting the mineral fertilizers during that time. So with no tillage, it means chances are there'll be no much that is being lost. I still really don't know much about it, and something I still exploring to understand what is happening.
Yeah. Thank you.
Just a comment to that.
Okay.
I mean, it could probably be the soil structure. So when you have no till, the water goes easier into the soil matrix and not the runoff. That would be my guess.
Yeah, I'm familiar on clay soils too.
Okay, so sorry, probably we will continue the discussions, but two last questions and we should finish. I think one is yours and later is yours. Please.
My question was, does the whole area look like this? So do you have already filter strips in the baseline, or are filter strips existing at the moment?
What?
So for filter strips, I was just wondering if the whole area looks like this, that you don't have filter strips, or do you already have them in your baseline in the calibration of the model?
No, in my calibration, I assumed as zero, no, totally no filters. But in the watershed, there are small pockets of within the filter, but we don't know the quantities of the amount that is available. So we didn't want to put it in our model because it was going to complicate it and bring a bit of confusion for us. So we decided to just assume there is nothing, and then what will happen if they all do it. But there are a few, maybe 10% of the area, but definitely some very, very small, 2-3 farmers, because a small area doing it. So.
And the last question?
So do you have any measurements on the soil test feed? Soil test phosphorus.
Soil what?
Soil testing or soil test phosphorus. Essentially the what kind of phosphorus level in your soil.
No, I don't have much information about the soil. Also, there was another colleague who you are working with who gave me the information from the soil. And what she was presenting, I think, one of the other presentations this afternoon also. So for the soil, she probably has that idea. So for me, what I was looking for more was the soil properties that are relevant for the SWAT modeling, and that's what I took from that. And also we understand this being clay soil, there's really a lot of the attachment of the clays compared to nitrates. That's why it's more nitrate issue than more phosphorus issue than nitrate problem.
Okay, so thank you.